is to introduce different ways to encode information, especially quantum information on photons, okay? So, of course, the unit, the informational unit in quantum information is the qubit. We know that the qubit, a single qubit state can be represented, geometrically represented in the Bloch sphere, where you can translate the coefficients of a general superposition into two angles on the sphere. So this sagittal angle and the azimuthal angle here. And the point is that to find physical systems where this kind of construction can be realized, can be represented physically, okay? So the most obvious one is the spin-half particle. Also, it's well known that in polarization optics, you can represent an arbitrary polarization of a light beam or of a single photon on a sphere, okay? But in the optical domain, this kind of representation existed even before quantum information, and it's called Poincaré. It's the Poincaré sphere, where you place all possible orientation of linear polarization on the equator and the circular polarizations on the poles, okay? And in between, you have all states of elliptical polarization. So again, this is quite interesting because the same kind of representation works for both for the single photon description, okay, or the quantum state of a single photon, but it also works for a classical object, which is the unit, the polarization unit vector, okay, in complex notation. So actually, this kind of representation is not exclusive of quantum description. Even in classical optics, it is used like that. And the meaning of the spherical parameters, theta and phi, are the same, okay? So, beyond that, you can also encode information, quantum information, on the path, on the spatial mode. In the spatial mode here, I mean the longitudinal wave vector, okay? So I can have, for example, a beam splitter, and if I have a single photon, the single photon has a certain probability to be transmitted, a certain probability to be reflected, and depending on this path here, it acquires a phase different with respect to the other path. So the general state of a single photon after the beam splitter is a superposition of two possibilities following the path 0 or following the path 1. The angle theta here is related to the transmission and reflection coefficients. Also, this phase here, phi, is related to the phase acquired in this extra path here, okay? And, but again, this same representation works for the classical wave function that describes the electromagnetic field. The difference here is that in classical electromagnetism, it makes sense to talk about half of the signal being transmitted, half of the signal being reflected. In quantum description, no. Either the photon is transmitted or it is reflected. And the state of the photon after the beam splitter is described by a superposition, okay? So it's very important that we see the same kind of mathematical description. This mathematical description can be used both in classical optics and in quantum optics, okay? And the difference between the two domains is not just a mathematical issue. It's a physical issue, okay? It's when detection, when observation comes into play is where there are the most striking differences between classical and quantum theory, okay? Now, let's go to the main subject of this lecture, which is how to encode information in a different degree of freedom, of a light beam, okay? And a different degree of freedom, which is intrinsically multidimensional, okay? So we start with this. Actually, what we are going to talk about, we'll be talking about, is essentially well-collimated beams, like this laser beam, okay? Which is the usual, how can I say, ingredient for quantum communication and in any optical experiment, okay? So we can ask ourselves, we learn in basic courses about plane waves. So this is obviously not a plane wave, okay? A plane wave is an object that is extended over all space. So it would occupy the whole universe. And this beam is transversely limited, okay? So how do we mathematically describe this kind of propagation mode of the electromagnetic field? So in order to do that, we start with the very basics of the wave function for the electric field, for example, okay? Now, we do, as usual, we propose a separated solution in which you have a spatial part, a time, an oscillatory time part, and a well-defined polarization vector, unit vector, okay? If we plug this kind of, this general form here in the wave function, in the wave equation, we obtain the Helmholtz equation, okay, for the spatial part, only for the spatial part. So this Helmholtz equation you obtain according to the boundary conditions that the light beam is restricted to. You obtain the modes, which will be the structures that will be occupied by photons in the quantum theory, okay? Here, we go one step further. We want to describe collimated beams. For Helmholtz equation, you can have spherical waves, for example, as a solution, and also, obviously, plane waves also. But none of them describes a beam, a well-collimated beam. So we go one step further. We assume that this spatial part has some very fast varying longitudinal function, like this one, okay, this oscillatory longitudinal function, and Z here will be, by definition, the propagation direction. And in the transverse plane, in the plane transverse to propagation, you have some function psi here, which is slowly varying in some sense, okay, which I will explain soon. So in this case, you have this part here that is slowly varying. I leave the possibility that this part also evolves, also changes with propagation, and I have to do that because I know that even if this beam is very well collimated, of course it diffracts a little bit, okay? It doesn't have the same extension close to the source and at the observation plane. So it changes transversely. So I leave this Z dependence here, okay? Now I will do the approximation that applies to well-collimated beams, which is the so-called paraxial approximation. So paraxial because the propagation, paraxial propagation means that you have propagation around a given axis in space, which is the Z-axis in this case. Now, the approximation is that when I apply this Laplacian here, okay, I will have, here I have a product, so I have to apply this Laplacian to this product here. And what happens if I apply this Laplacian, what we get is something like this. So this gives rise to this factor. This part here gives rise to a factor like this. And this one, I can write this way. Okay? So what happens here is that the assumption that we make is that this function varies along z, but very slowly. Note that this one, this part here, is multiplied by k. So you have the comparison that we are making here, we have to make here is this, between this with 1 over lambda, the wavelength, and the first derivative. Okay? So what we say is that, since this beam will not vary, how can I say, the scale at which it varies is in meters, along meters, and the wavelength is microns. So this term here can be neglected when compared with this one. So we get rid of this part, and we end up with this equation. And this is the paraxial equation. Okay? So this kind of well-collimated beam is a solution of this part here. So does anyone recognize this kind of equation from quantum mechanics? That's the Schrödinger equation, okay? It's exactly the Schrödinger equation. Actually, it would be the Schrödinger equation for a free particle in 2 dimensions, okay? It's the Schrödinger equation. So I will use this kind of analogy very often so that I can get your intuition from quantum mechanics to this classical optical context, okay? Now, here it comes. What is the basic, the simplest solution of this equation is the fundamental Gaussian mode, okay? Is the Gaussian wave packet. Now, imagine the Gaussian wave packet. Note that it's very important that who is playing the role of time here is the longitudinal propagation, okay? Direction, okay? Z, the longitudinal coordinate. So the Gaussian wave packet, what happens, it is a solution, of course, it's a solution. And we know that for a free particle, if I prepare a free particle in a Gaussian wave packet with time, it diffuses. And that's diffraction within the paraxial limit. So the diffraction in the paraxial limit is formally equivalent to the Gaussian packet diffusion in quantum mechanics, all right? So this, you will have this kind of this is the real part, is essentially a Gaussian. The width of the Gaussian is not constant. It varies with the propagation. It's diffraction, and it's equivalent to the quantum wave packet diffusion, okay? And the evolution of the beam width will occur like this. So the beam has a minimum width plane, which is called the waist, because it's our minimum cross-section, okay, which is the waist of the beam. At this minimum waist, or this waist or minimum width, we call it this W naught. And the diffraction occurs in a scale, in a distance, a characteristic distance, which is related to this minimum width. And this distance is the Rayleigh distance, okay? So we see that the larger the minimum width, the larger the Rayleigh distance, okay? So if the wave packet is larger, very large, it will diffuse in a long time, okay? If you localize like a delta function, it will immediately explode, okay? So it's the same kind of intuition from quantum mechanics and from diffraction theory within this scalar limit or paraxial limit, okay? And we have also this complex part here that has this, that describes the fact that this kind of solution does not even have a plane wavefront, okay? So it's a curved wavefront, and the radius of curvature is not constant, it varies along propagation, okay? It goes to infinity, so the wavefront is plane on the focal plane, okay? And in the at infinity, so it arrives at a minimum value. So there is, as it propagates, the curvature changes, gets to a maximal curvature, and then it tends again to a plane wave, very far from the source, or very far from the focal plane. So this is the basic solution, but what if we try to find other solutions, okay? Can we find other solutions to this equation? So the answer is yes. So actually, depending on which kind of coordinate system that we use to solve this equation, we obtain a different family of orthogonal solutions, okay? If I use rectangular or Cartesian coordinates, I get the so-called Hermite-Gauss solutions, okay? If I solve it in cylindrical coordinates, then I have the Laguerre-Gauss solutions, okay? And now, I will use again, so that they just don't appear like that from nothing, okay? I will use the quantum mechanical analogy again. Why are these solutions of it? So actually, this kind of product solutions between Hermite polynomials and Gaussians occurs in quantum mechanics for the solution of a harmonic oscillator, okay? The wave functions, the eigenfunctions of the harmonic oscillator are essentially Hermite polynomials times Gaussians. So what happens here is that the fundamental Gaussian beam would be like, I have at t equal to 0, a harmonic oscillator in the fundamental state, okay? And then at t equal to 0, I switch off the potential, make it free, and then it diffuses. The other solutions would be exactly the same situation, but at t equal to 0, instead of being the fundamental, I would be in the first excited state. Now suppose I have a harmonic oscillator in the first excited state, and at t equal to 0, I switch off the potential. Then, at this time, you have the Hermite Gaussian function. Of course, it will evolve, it will diffuse, but it will keep this Hermite Gaussian shape as it diffuses, okay? So this is the same situation. And for the other levels, it will be, remember that I said that this is the equivalent to a two-dimensional particle, okay? So this would be the harmonic oscillator in 2 dimensions. Go ahead. Mm-hmm.
But here you have a free particle.
Yeah, you see, no, wait. No, you don't have any quantization. You see, my point is that the quantization condition is for stationary states. When you have the potential, these wave functions are stationary. When you switch off, they are no longer stationary. It diffracts, it diffuses, okay? So you have, these are not the only solutions for a free particle. You have many, and time-dependent, okay, solutions. The only stationary solution for the free particle is the plane wave. But you have other solutions that are confined, they are not stationary. You see the point? Okay? So these are not stationary solutions of a free particle. It's a time evolving, they are time evolving. So, and of course, if you look at the other possibility, which is the solutions in cylindrical coordinates, this gives rise to the so-called Laguerre-Gauss solutions. They are Laguerre polynomials times Gaussians, okay? And quantum mechanically, they would be what they are what you would obtain if you diagonalize the Hamiltonian and the angular momentum of the particle in 2 dimensions. Okay, so you now quantize a particle in 2 dimensions. Okay, suppose you quantize a particle in 2 dimensions, and you look for eigenfunctions of both the Hamiltonian and the angular momentum of this particle. Then you get these eigenfunctions, which are Laguerre-Gaussian eigenfunctions, but of course, these are modes that they have some kind of vorticity because they have well-defined angular momentum.
Yeah, in this case, you have boundary conditions that impose some quantization, right?
Yeah, but look, the equivalence here is that now what is going to happen in optics is not equivalent to the confined particle. Is equivalent to what happened to the particle as you switch off the potential.
No, but I mean, if you have a free particle and you put boundary conditions in a box, then appears the quantization.
Okay.
You have free particle, and there is a boundary condition because of the rotation.
No. Well, here you don't have any boundary condition, not even the rotation. And still you have confined solutions. But they are not eigen solutions. They are not stationary solutions. Okay? You are not forbidden to propose a discrete set of solutions for a free particle. Okay? You can have discrete solutions for the free particle, but they are not the only solutions. The problem is that when you have confinement, these discrete solutions are the only stationary solutions. Okay? It's very important. You don't have any other option if there is confinement. Okay? So here you have the eigenfunctions that you obtain when you diagonalize both the Hamiltonian and the angular momentum. Okay? And you have a whole family of these modes. Okay? Now, let me now put some general properties of this mode. So the Hermite-Gaussian modes, they look like this. Remember, they are modes in 2 dimensions, so I have Hermite polynomials on both x and y, and Gaussians, okay? I have, again, the curved wavefront. I have something here, which is an extra phase factor along propagation. It is always also there for quantum mechanical system, okay, for a free particle, okay? And this one is called the Gui phase. What is interesting is that, so these solutions, the Hermite-Gaussian solutions, they are orthonormal in this formal scalar product here, okay? They are orthonormal, and also they constitute a basis set. Any square integrable function in 2 dimensions can be expressed in terms of these Hermite polynomials, okay? So this is the closure relation, not written in bracket notation, but written in wave function notation, okay? So this is the closure relation. And also, we can make a hierarchy of these solutions on something that I call the order of the mode. So the order, so these solutions, they are indexed, the Hermite polynomials, they are indexed with an integer number, m, with a natural number, m, n, a pair of natural numbers, m and n, and the addition gives you the order of the mode, okay? So the fundamental mode is 0 and so on. So each order will define a subspace of modes, okay? A subspace of modes. I will turn to this point later. So I can also solve the paraxial equation, but in Cartesian coordinates, but with rotated frame, okay, with a rotated frame, and of course I will obtain rotated Hermite-Gaussian modes like this. The same properties apply to, they are of course, they are orthonormal, complete, they carry the Gui phase, and the same the same applies to the Laguerre-Gauss modes, okay? Now, the Laguerre-Gauss modes, they have just this subtle point, which is the order is related to the indexes of the mode in two ways. You have twice this mode, twice this number here, P, plus the absolute value of L. What are the meanings of these two numbers here? First, L. The L determines the phase, the azimuthal phase dependence of the mode, okay? And it is here. It's also very commonly called the topological charge of the vortex beam, okay? And the P will define, will govern the radial behavior, and as P goes from 0 to 1, you get rings around the mode, okay? So this P value is responsible to present rings in the solution.
Just one question about the green phase. It looks like it vanishes as you go too far compared with the radially.
No, wait a minute. No, it goes to pi over 2. It does not vanish. So if it goes to infinity, the arctangent is pi over 2. Yes, it tends to pi over 2. This part here varies from 0 to pi over 2. And it's pi over 4 right at the radial distance. But note that this is a phase that is multiplied by the mode order.
Does it, the fact that it gets, does it has anything to do with the, because it's a small when you're close to the base and it sort of gets constantly, does it have anything to do like to an uncertain?
Well, I don't know if I understood the question first, but yeah, go ahead. You have another question. Okay, so I thought you wanted to comment on that. So you are trying to relate the GUI phase, the fact that it's 0 at the focal plane with what?
No, I'm just thinking like, why is it, it seems like when you are restricted in space, it sort of vanishes, and as you expand, it grows bigger.
Well, actually, what happens is that some people interpret the GUI phase. There are many different interpretations of the GUI phase, okay? Some people interpret the GUI phase as a kind of consequence to the fact that the wavefront is curved, okay? So somehow it's not like, it's like the GUI phase is responsible because you adopted, you assume that you have this fast dependence here, okay? So the GUI phase is, you can think of it as a correction to the wave vector, to the longitudinal component of the wave vector, which should be larger. This correction should be different for each mode order. I think that this is the best way to think about that. They are not eigenfunctions in the sense that they are not eigenfunctions. Eigenfunction is stationary, okay? They are solutions of the full paradoxical equation. It's like we don't call an eigenfunction a solution of the time-dependent Schrödinger equation, okay? We call an eigenfunction a solution of the time-independent wave equation, okay? So always you must keep in mind, in order to not to misuse this quantum analogy, you must keep in mind that the equivalence here is between the time-dependent Schrödinger equation and the paradoxical equation. No, it's not a simple change of coordinates. No. Okay? No, it's not a simple change of coordinates. Okay, good point. So, so because of this part here, okay, this topological chart, it's very interesting to call your attention to one fact, okay? You see that the topological charge of the mode appears in 2 points of the solution. One point is here at the azimuthal phase dependence. And one point is here, the other point is right here. Well, it is here also, but it's not very important here. The important point is that part here, because it's a monomial. So every time you have azimuthal dependence, you have this monomial that, that warrants that the solution vanishes at the origin. Okay? So note that the azimuthal coordinate is not well defined in the origin. So there is a very interesting question, is what time is it in the North Pole right now? What time is it in the North Pole? Okay? All points on the Earth that are on the same meridian, they are on the same time. But all meridians, they meet in the North Pole. So actually, the North Pole as the South Pole, they are both time singularities. Okay? They are time singularities. There's no time defined there. In the same way, the phase, not the phase, but the the coordinate phi is not well defined in the origin of this cylindrical coordinate system. So it's not defined there. This part here is not defined, but we don't have to bother because this part here warrants that there is no energy there at that point. Okay, there is no energy there. So actually, this topological charge, yes, sure.
Discussing the Hermit Gauss beams, you talked about rotations and how the beams change with rotations. In the Laguerre Gauss, they seems invariant by rotations on the x-y plane. So what kind of transformations you can perform in those beams?
Okay. Well, you can think about polarization, for example. So what happens is that if you have circular polarization, any polarization rotation would do nothing to. However, this is not the most general operation that you can do. You can, for example, if you have a superposition of 2 modes, you can dephase these 2 modes. Okay? So actually, what the transformations that you make in the Laguerre-Gauss basis, they become more evident when you have superpositions of them, not in single. If you think about the particular operation of rotation, which is just one possible unitary operation, and it's true, the Laguerre-Gauss modes, they are eigenmodes of this kind of operation, so they are invariant. Okay, but you have other operations. Now, the main point is the following here. So regarding Laguerre-Gauss modes, the interesting point is that the wavefront, their wavefront shape is a helical surface, like a fusilli pasta, okay? So this means that the Poynting vector, as well as the wave vector, the complete wave vector, spiral along propagation. And this spiral configuration of the Poynting vector makes that the energy flux in such a mode rotates along propagation. So this is why this kind of solution carries orbital angular momentum. So a light beam, besides carrying spin angular momentum for circularly polarized mode, it also carries orbital angular momentum in the whole structure of the wavefront, okay? In the whole distribution of the wavefront. So in this paraxial regime, now there is an equivalence between paraxial propagation and non-paraxial propagation and relativistic and non-relativistic quantum mechanics. So for in relativistic quantum mechanics, you cannot separate the angular momentum of an electron into an orbital part and a spin part. It is only valid for non-relativistic quantum mechanics. In the same way, for paraxial propagation, you can separate the spin part and the orbital part, okay? You can separate spin part and orbital part, but not in the full diffraction theory beyond paraxial propagation, okay? So in this paraxial regime, we can interpret the angular momentum of the electromagnetic field as being carried in 2 different degrees of freedom, polarization and the wavefront structure. And this is what we are going to use to encode information, okay? Now, experimentally, how do we reveal that a beam has this kind of phase structure? So this is the intensity distribution, okay, of L equal to 1, Laguerre-Gauss mode. This is the phase distribution that we can obtain by superposing this mode with a regular Gaussian or a plane wave, okay, or an approximately plane wave. So if we superpose them and look at the diffusion fringes, the constructive in destructive interference, fringes appear, they show themselves as spiral, as a bright spiral intertwined with the dark spiral, okay? So this is calculated, and this is experimental result, okay, that I can obtain by mixing them in a beam splitter, a Gaussian mode and a Laguerre-Gaussian mode, all right? How do I generate these modes in the lab? I have essentially, nowadays, we do this by using holograms, okay? So if I have this, this is the Fresnel lens, so the old guys like me who defended their thesis in the old projectors, okay? These old projectors, they employ Fresnel lenses because it's what you use whenever you need to focus a very large beam, okay? And so lighthouses in island, okay, in the sea, they employ Fresnel lenses, okay? So this is a Fresnel lens. If you break the rotational symmetry in a Fresnel lens with this kind of spiral Fresnel lens, so besides focusing the beam, it imprints a twist on the wavefront, okay? And then you can recollimate with a regular lens, and what you get here is a Laguerre-Gauss mode, something that resembles a Laguerre-Gauss. You get an optical vortex. Or you can diffract a Gaussian beam in a almost regular diffraction grating, but one that carries a topological defect here. So if you center the Gaussian beam in this topological defect, the diffracted modes are optical vortices with opposite helicities, opposite angular momentum, okay? The Hermite-Gaussian modes can also be produced in this way, but in this case, what we do is to shift half of the diffraction grating by half period, okay? So, and we center the Gaussian beam here, so the orders, they resemble Hermite-Gaussian modes. Go ahead. Yes, at once. Yes. You generate all of them at once. They are the diffraction orders. However, of course, you can do what we call blazing. So you can break the lateral symmetry of the grating in order to maximize the energy transfer to one diffraction order with respect to the other one. Okay? So these are experimental results for example, for this kind of grating. Mm-hmm. Now, the interesting part is that when, of course, you have different mode families, okay, but they are solutions of the same equation, the paraxial equation, and of course, each one of them constitute a basis. So it is possible to express one family with respect in terms of the other family, okay? So you can, for example, write a Laguerre-Gaussian mode as a superposition of Hermite-Gaussian modes, okay? Now, the interesting thing is that this transformation is block diagonal in the subspaces defined by the orders. So it is closed within each order subspace, okay? So Laguerre-Gauss modes of, let's say, second order, okay? Like this one, third, this is 0, 1, yeah. Of this, these here, okay, they will be only superpositions of Hermite-Gauss modes of the same order. Okay, so this means that the transformation is restricted, is closed in each subspace. This is manifested in this formal. So what happens is that the complete unitary transformation between the two mode family, they are, how can I say, direct additions of unitary transformations within each subspace. Okay? So actually, you can realize a symmetry, an SU-N symmetry. So for polarization, we are restricted to SU2. But now here, we can realize SU-N at each subspace. If I restrict my attention to these modes here, I will realize an SU2 symmetry. Okay? So it's an extra SU2 symmetry on the top of the one given by polarization. If I go to the third order, or second order, then I have the SU3 symmetry, and so on. Now, actually, this kind of transformation between the two modes is not, between the two families, is not only a formal mathematical operation, it's something that you can do in the lab. Actually, you can make the transformation. And this is a stigmatic telescope, if you want, okay? You have a pair of lenses, one that focuses and the other one that defocuses the beam, but not regular, not spherical lenses, but cylindrical lenses. What happens is that because of the Gouy phase, okay, the focalization changes the Gouy phase, and because of the Gouy phase that depends on the order of the mode, okay, what happens is that, suppose that I have a vertical Hermite-Gauss mode, and I send to a mode converter or this cylindrical telescope that is oriented at 45 degrees. Then along the propagation, I can think of these vertical Hermite-Gauss modes as a superposition of these two, plus 45 and minus 45 Hermite-Gauss modes, and within the mode converter, they acquire different phases. And after passing here, they acquire a pi/2 phase, an I factor. An I factor that transforms this mode into a Laguerre-Gauss mode. All right? So it's equivalent, for those working with optics, it's equivalent of a quarter wave plate. So you have the fast axis, the slow axis, okay? This would be equivalent to the 45 degrees orientation of the mode converter and minus 45 degrees, okay? If you arrive with polarization in the middle of the two axes, the fast and the slow, then you have the transformation to a circular polarization. So this is the same, exactly the same. You can do more. So this is the kind of thing that we have been using there, just to illustrate what kind of research we do in our lab. So we wanted to actually use a tomographic technique to given a general superposition of a given order, okay? Given a general superposition of a given order, we wanted to obtain, to find from measurements, from intensity measurements, the coefficients of the superposition, okay? And actually, because of the symmetry, there is this kind of superposition has this intrinsic symmetry. Actually, if you have an image of a superposition of a given superposition of modes, for example, in this case, this is the third order, okay? So this is third order modes. There are 4 independent modes here. A superposition like that. Actually, you have a different superposition that gives you the same image. So from direct image, you cannot distinguish between them, okay? And but however, if you acquire 2 images, one direct and the one that is transformed by some astigmatic transformation, like a mode converted, but in our case, we did something simpler. We just put a spherical lens, and we tilted the spherical lens, okay? And then you get the astigmatic transformation that you want. And this astigmatic image reveals the difference between the two. It lifts this kind of degeneracy of the image information, okay? Actually, we did this with the machine learning, so we trained the machine to recognize the superpositions from pairs of images, okay? Of course, because of this ambiguity, the machine would not be able to recognize just from one, okay, image. However, if your superposition you restrict only to positive angular momenta, then only one image you can identify the superposition, okay? So now, we arrive at the sensitive point of this talk. We can build 2 Poincare spheres to describe, for example, a first order mode, okay? So let's suppose that we are going just to analyze that subspace of first order Hermite-Gauss and Laguerre-Gauss modes. So actually, this it also has the mathematical structure of a qubit. It's the same structure of a qubit, and it can also be represented on a sphere, on a kind of Bloch sphere that, in the jargon of people working with structured light, we call it the orbital Poincare sphere. So we have a spin Poincare sphere and an orbital Poincare sphere. Again, as I said, in classical optics, we have unit vectors, polarization unit vectors, and they obey the same kind of transformation as qubits. The mathematics is the same. Here, I call psi h and psi v the horizontal and vertical first order Hermite-Gauss modes, and they also can be combined with some coefficients like that, okay? So this is also a classical optics object, okay? It's just a wave function from classical optics. And now comes how do I build the combined space of modes when I use both the orbital part of the beam and the spin part of the beam. So if I combine these transverse modes with polarization, what kind of mode structure do I have? Actually, this is done in the mathematical procedure is the same that you do in quantum mechanics when you combine the state space of 2 independent qubits. You make the tensor product, okay? So actually, in classical optics, we can talk about separable and non-separable structures, okay? So we can do the tensor product between the space of orbital angular momentum modes and the space of polarization modes. And then you can think of structures that are like this. So I can think of general first order spatial mode, which is an arbitrary superposition of first order Laguerre-Gauss modes, if you want, with a general polarization, okay, which is the same polarization for the whole beam, but it's arbitrary. This would be a factorized mode. But now, of course, I can think of structures that cannot be factorized. They cannot be written in this way. And the examples are these. For example, a very simple example. I take horizontal Hermite-Gaussian with horizontal polarization and superpose with vertical Hermite-Gaussian and vertical polarization. I can do it with plus and minus, or I can have the polarization crossed with respect to the Hermite-Gaussian orientation, with a plus and minus. So I have 4 kinds of modes that cannot be factorized, and they are equivalent. They are mathematically, formally equivalent to Bell states of 2 qubits, okay? So for this reason, I call them Bell modes. Actually, you can borrow more concepts from quantum information. For example, you can given an arbitrary superposition of all combinations of psi h and psi v with EH and EV, given a superposition like that, this tells you this quantity here, which is the concurrence, a lot used in quantum information theory to decide whether a pure state of 2 qubits is entangled or not. You can use the concurrence here, you can borrow this concept for quantum information, to quantify the non-separability of the 2 degrees of freedom, even in classical optics. Okay? So it's just a property of, it's just a property of tensor product spaces. And it's not exclusive to quantum mechanics. Again, quantum mechanics makes a difference in the observation. Okay, measurement. Measurement is different. Go ahead. Just a mathematical analogy. Okay? Now, what's the meaning of this non-separability? That's the main point. What's the physical meaning, after all, of having a polarization spatial structure that cannot be factorized? The meaning is a set, the 4 Bell modes. They are modes in which the polarization is not uniform over the wavefront. It changes from one point to the other. Okay? Actually, this HH plus VV, it presents this kind of polarization configuration. The polarization points radially. And because of that, it's called the radial polarization. Okay? This one, phi minus, is the azimuthal polarization. Those 2 are called counter-rotating. And the reason for that is because as you go around the beam, this one and this one, and this one and this one, the polarization rotates at the same sense. Okay? So if you rotate counterclockwise, so does the polarization. For these 2, it's the other way around. When you rotate counterclockwise, the polarization rotates clockwise. So these 2 are called counter-rotating, and those 2 co-rotating. Okay? And we can, fortunately, we can easily produce them in the lab. We have available, commercially available, these S-plates that you can buy, and from a Gaussian beam with the correct polarization, instead of just doing what a quarter wave plate do, you can think of it as especially, you can think of it as a half-wave plate, but in which the fast and slow axis vary point to point. So you arrive with a given polarization, and then the polarization is rotated differently for each point. At the output, you have this polarization pattern. Again, it's a vortex, okay? All points at the same radial direction, they have the same polarization. And all radial directions meet right here at the center. So there is no energy there. Okay? The amplitude, the field amplitude there is 0. Now here you don't have a phase singularity, which would be a singular, scalar singularity, okay, a scalar vortex. Here you have a vector singularity. So it's called a vector vortex. And in the literature, many people call it a vector beam. So that's the point. We can, of course, for a general mode, spin orbit mode, we can combine both. We can, for example, define we know that from classical optics, we define the degree of polarization with the Stokes parameters, okay? We have the Stokes parameters. They are used also in quantum tomography, okay? You calculate the Stokes parameters by measuring the qubit in different unbiased bases, okay? And then the same is true here. Given an arbitrary polarization, we can make projections in linear horizontal vertical polarization, linear diagonal anti-diagonal polarization, or right circular and left circular polarization. With this, we obtain all the Stokes parameters, okay? For partially polarized light, completely unpolarized light, you would get all of them equal to 0, for example, okay? As for a qubit p pair in a completely mixed state, it has the density matrix is proportional to the identity, so you don't have anything, okay? Any coherence in any basis. So the same is true for the orbital part. Now, to measure this, we do polarimetry. For the polarization, we do polarimetry. I have a polarizing beam splitter that transmits horizontal polarization, reflects vertical polarization. With the polarizing beam splitter alone, I will measure this guy here, S1. If I precede the polarizing beam splitter by a half wave plate or a quarter wave plate, I can measure S2 and S3, okay? And what we get is that S1 square plus S2 square plus S3 square is smaller or equal to 1. If it's 0, it's completely unpolarized. If it's something in between, it's partially polarized. If it's 1, then it's fully polarized. You don't know how, maybe elliptical, maybe whatever, but if it gives 1, it's fully polarized, okay? Now we can do the same in the orbital part, okay? We have this kind of device that we can use to sort spatial modes. Actually, this is a Mazender interferometer in which one of the arms, you introduce an extra mirror, so you have an extra reflection. What happens is that Hermite-Gauss modes that are horizontal, the two lobes of the Hermite-Gauss modes, they have a phase difference of pi. So every time you make a reflection in the horizontal plane, it adds a pi shift to the mode, okay? Because you change the right lobe with the left lobe, okay? They are exchanged, so this amounts to a pi phase shift. The vertical one is not sensitive to reflections in the horizontal plane, because this is the symmetry. It's symmetric with respect to this reflection, okay? So this is also true for the polarization, okay? Horizontal polarization in a reflection changes phase. The vertical, no, doesn't, okay? So the combined, by making this kind of interferometer with the two arms balanced, so in terms of wavelength, the lengths in terms of wavelength are equal, or they differ by an integer amount. So if the two paths are balanced, we have at the output the sorting of polarization and Hermite-Gauss modes, like this one. Okay, so if I have HH and VV, they will both go through one part, because this one never acquires any phase in the reflections, always 0. This one acquires phase, but it acquires the pi phase shift twice, one because of the polarization and one because of the transverse mode. But if you have to acquire pi phase shift twice, it's 2 pi, it's nothing again, okay? And so at the output here, they will interfere constructively in this arm. So they will go out through this arm. And the other combination will go out this way, okay? Now, we can do something that is only sensitive to the spatial part. How do we do this? We put a wave plate, a half wave plate, inside the interferometer, so that in this arm here, this half wave plate will add a pi phase shift only to the polarization part. So then, this the extra pi phase shift acquired in the reflection here is erased in the balance because of the polarization phase shift here, but not the spatial part. Now, this kind of interferometer with a wave plate inside works as a mode, a spatial mode sorter for first order only, okay? So it works as a mode sorter, okay, which is insensitive to the polarization. Now, what's interesting is that we can use this device exactly as this will work. This here is equivalent to the polarizing beam splitter, but for Hermite-Gauss modes. It's in the lab, we call it a TBS, a transverse beam splitter, okay? So we have a PBS for the polarization and a TBS for the transverse mode. If I precede the TBS with a mode converter, which is equivalent to the wave plate, half or quarter wave plate, then I can measure all Stokes parameters of this kind of structure, okay? But only the orbital part, okay? Now, this is equivalent to doing tomography in quantum mechanics. Now, in quantum mechanics, you have some general density matrix that you can write this way. This density matrix is represented by some point in the volume, not in the surface, because the surface are only for the pure states. But in the volume of the Bloch sphere, you have a general density matrix, okay? By making measurements, projective measurements in a set of 3 mutually unbiased bases, okay? You can have the Stokes parameters that determine all the parameters that define the density matrix. So you can reconstruct the density matrix. This is how it works, okay? Or it's equivalent to quantum state tomography in quantum mechanics. Now, what if we do polarimetry? So the point here is that I will measure the polarization Stokes parameters of one of these vector vortex beams. What should it give to us? What should it give to us? So what happens is that we know that if this quantity is equal to 1, we have something fully polarized. If it's smaller than 1, it's partially polarized. If it's 0, it's completely unpolarized. So completely unpolarized is like the light from a lamp. It's some random source, okay? Now, what is interesting, that we can do the measurement, the Stokes measurement in this kind of structure, this radially polarized beam, and what you obtain is 0. You obtain the value that is expected to random polarization. Come on, it's not random. It's not well defined, okay? It's not well defined, but it's not random. It's a well-established configuration of the electromagnetic field. But it gives you the Stokes parameter that are 0, okay? How do we understand that? Again, we need quantum information intuition, okay? So the point is that if you try to do the orbital tomography also, it gives 0. Like there is no kind of spatial mode in this object here, okay? But then we go to quantum information to understand what's going on, okay? So suppose you have a pair of qubits and you are going to do, okay, tomography on only one side. You are only doing tomography on one side. So what you are doing, you are reconstructing the partial trace of the whole density matrix, okay? And if the complete set of the 2 qubits is in a pure, maximally entangled state, then we know that as you do the partial trace, the local density matrix of a single qubit is a a complete mixture. It's proportional to the identity. So the whole structure, the whole pair of qubits is in a pure state, but locally it looks like a complete mixture. And this is what is happening here, okay? So actually, because the polarization and the orbital part, they are completely non-separable, even in classical optics. If I try to do polarimetry, looking only to 1 degree of freedom, I obtain the results expected for random distribution of that degree of freedom, even if the whole structure is completely coherent, okay? So this is this explained, okay? Actually, if we calculate the intensities that I define in the Stokes parameters, okay? They are projections of the field structure, of the field configuration in given polarization unit vectors, the polarization unit vectors associated with the analysis that you are doing in the measurement, okay? And then, actually, this integral here is very interesting. I suggest you to do the exercise, okay? It's a good exercise. By using the formal equivalence between the classical and quantum description, you can write this intensity here exactly like this, in this way, which looks like a partial trace. It's a spatial partial trace, okay? The detector, see, if the detectors are big, are large, they swallow the whole beam, okay? You don't get spatial resolution, so it's like you are tracing all the spatial part, and when you trace the spatial part, the polarization part appears to you as something incoherent, okay? And the same for the orbital part. The orbital part also you can calculate the intensities that you measure here as a polarization as a partial trace over the polarization part. Okay. Now, another interesting consequence of a maximally entangled state, okay, maximally entangled state in quantum mechanics, is that if I have a pair of qubits in a given maximally entangled state, and I make a projective measurement on one of them, then this the other qubit will be projected also to a given state that depends on the projection that occurred in the first one, okay? So the projection in one qubit is followed by a projection on the other qubit, okay? What does it mean here, okay? So suppose I have some mode like this, okay? And I will do this a partial projection. I can either, for example, I can first select a small part of the spatial distribution here, and then I do polarimetry. If I select a small part of the beam and then I do polarimeter, then I see the Stokes parameter raise again. Then I will see actually the polarization, how can I say, degree of that part of the beam, okay? So I recover the coherence of the polarization part by restricting my observation to a given spatial part of the beam. Now, it's also interesting, okay, that, for example, suppose you have a 2-qubit that is in this way. Now, I define the rotated bases, theta and theta prime, like this, for a qubit. And actually, this kind of state, for any orientation theta, it will appear like that. So, if I project if I make a projective measurement in one qubit along a given direction theta, the other qubit should be projected at the same direction, okay? Now, what means here for the vector beam? Actually, if I define the two rotated bases here, the unit vector rotated bases, and also the rotated mid-Gauss modes defined like this one, okay, given by this one. So then I can show that actually this mode here, this spin orbit mode, psi plus, which is HH plus VV, in any orientation, it will be like that, theta theta plus theta prime, okay? Actually, you can show that very easily. It's just enough to write down this expression by substituting those two here, and you see that all dependence on theta goes away. So it's invariant, okay? Now, how do I see this experimentally? Now, what I'm doing here, I'm preparing a vector beam. I'm passing through a polarizer, okay, that I'm going to rotate. And with a camera, I register the image that is transmitted through the polarizer, okay? So, as I project the polarization in a given angle, the spatial part is projected to the mid-Gauss mode at the same angle. This is experimental. It was done experimentally, okay? So you see, we rotate the polarizer, and we see that the beam transmitted is a rotated mid-Gauss mode. So it's the same thing. You have a maximally entangled 2-qubit state. You project 1 qubit in a given direction, in a given superposition, the one is projected the same superposition, okay? I can also use it to transfer our angular momentum, okay, to generate angular momentum. Actually, in that mode, there is hidden, you can, for example, produce orbital angular momentum. That mode doesn't have any angular momentum, neither spin nor orbital, but you can generate by making projections in the polarization part. So suppose you have this kind of mode, now HH plus VV, but with an I factor here, okay? And then what you see is that actually I can use the Laguerre-Gauss decomposition for these modes here, okay? Laguerre-Gauss decomposition for the spatial part, and I use linear decomposition for the polarization part. And we see this way. So what happens is that there is a given orientation of the polarization filter that such that the transmitted beam will carry orbital angular momentum. So the experimental result that we obtain is like that. So we have a radially polarized beam that first passes through a quarter wave plate. This quarter wave plate will introduce this I factor here. So the radial polarization is HH plus VV without the I factor. But as it passes through the quarter wave plate, it acquires this I factor here. And then, okay, I have a polarizer that will filter one polarization. Okay, actually, from this expression, I see that depending on the direction that I filter, I can obtain plus or minus angular momentum, okay? And you see angular momentum, it loses angular momentum, and now it acquires the opposite angular momentum, just from polarization filtering, okay? So, with that, we arrive at the end of this lecture that was essentially devoted to convince you that beyond path and polarization, we can encode superpositions and blosphere-like representation in the spatial part of a well-collimated beam, of a paraxial beam, okay? This is a high-dimensional degree of freedom, okay? But still, it's not a high dimension that you do not control. It's a high dimensional that you can organize in subspaces, and you have experimental devices to operate within these given subspaces, okay? And you can combine this kind of spatial structure with polarization, and on the next lecture, we will discuss what are the physical consequences of this combination, and essentially how it can be useful for quantum communication, okay? But with that, I thank you for your attention.
I'd like just to ask if the idea that we can construct qubits with the first order modes is it's the same as we go to higher modes. For example, we have like in second order modes we would have like qubits, and then that scales in the same order.
Yeah, it works. Yes, it works. You can encode Q-treats, Q-quarts with transverse modes. Actually, instead of using these holograms that I showed, they are now employed. They are not now. They are employed with the spatial light modulators, which are devices in which essentially they are mirror screens that work as a mirror, but it's pixelized. And you can electronically change the index of refraction of each pixel, and with that, you generate a spatial modulation of the wavefront of a beam, of an incident beam, and this spatial modulation can be programmed. So it has an interface with the computer. You can program the kind of hologram that you want. So I can produce a hologram to generate second order mode, third order mode, first order mode, whatever you want, actually, okay? And it's programmable, and you can even change it in time, in real time, okay? For the spatial light modulator, you have larger efficiency in doing that, but the modulation speed that you can apply is limited. It's not a fast device. However, you have the DMD, which is a digital mirror device, in which each pixel, instead of changing electronically the index of refraction, we change the orientation. It works like mirrors, okay, small mirrors, micro mirrors device, actually, and you can change the orientation. The problem with that is that you have less efficiency, you lose power. However, you can modulate very fast, okay? You can go like kilohertz or more than this, maybe hundreds of kilohertz. Questions, other questions? Okay. Okay, thank you.